robustly packed learnable with respect to U if for all epsilon there exists a sample size and the learning rule A such that for all distributions D over X and Y, the learning rule will output a predictor that is at most epsilon worse from the best predictor in the class in terms of robust risk. So now, as in standard pack learning, we want to know which classes H can we actually robustly pack learn. In particular, can we robustly pack learn VC classes, which are hypothesis classes with a finite VC dimension? Okay, so how can we ensure that the population robust risk is small? Well, a natural approach is, given a sample S from the distribution, let's just pick a predictor H in the class that minimizes the robust empirical risk. And there has been recent work studying computational approaches to solve this robust ERM problem. But of course, what we really care about is the population robust risk. And so we need to establish a concentration guarantee. This has been the subject also of some recent work that tries to, that establishes uniform convergence of the robust risk. It studies this under various conditions, with special interest in the deep learning case for neural nets. Unfortunately, there seems to be empirical evidence that suggests that the robust risk might not concentrate as well as the standard risk. And there could be a large gap between the empirical risk in the robust case versus the population robust risk, even when the standard risk, the standard 0-1 risk concentrates very well. So in fact, for our first result, we show that there is a very simple hypothesis class H with VC dimension 1, where we do not have uniform convergence of the robust risk, no matter how large of a sample that we draw from the distribution. More so, we show that robust ERM fails to robustly pack learn this class H, even in the realizable case, where we know there exists a predictor that is perfectly robust on the distribution. We even show that no proper learning rule can robustly pack learn H, and this includes basically any M-type estimation rule or any rule that is constrained to outputting a predictor in the class H. Okay, so does this mean that we can't really do robust pack learning and we basically this won't work for VC classes? Well, surprisingly, we find out that it's actually possible to do robust pack learning. We just need to be improper. So we show that for any adversary U and any VC class H, there is an improper learning algorithm that can robustly pack learn H. The algorithm, just to remind you, an improper algorithm is not constrained to outputting a predictor in the class, so we can go outside the class. I'll briefly describe the approach, but for more details, please attend our poster session tonight. And before I start, also I should say that this approach relies on amazing recent progress on sample compression schemes. So we'll start with the realizable case. So to remind you, the realizable case, we know that there exists a predictor in the class H that is perfectly robust on the distribution. So what happens is we receive a sample S from the distribution D. The first step, we inflate this set S to include all possible perturbations under this adversary U. Now this is a potentially infinite set, but we show that we can actually discretize this set to a finite set that includes just the original points plus a finite number of perturbations, using arguments based on Sauer's lemma and the dual VC dimension. And then once we have this finite set, we feed it to a boosting procedure that uses a robust ERM as a weak learner. And our final output is a majority vote over predictors in the class H. And so this is an improper learning rule. So we establish robust generalization guarantees through sample compression argument. And this is based on recent work by Moran and Yehudayev and Haneke, Kontarovich, and Sadigarsky. For the agnostic case, we showed that it can be reduced to the realizable case, also following an approach by David, Moran, and Yehudayev. So let's compare standard learning and robust learning. In standard learning, we know that proper learning, in particular with ERM, is always possible. So, but in case of the robust learning, we show in our work that sometimes we need to do improper learning. For standard learning, we also know that, for pack learning, finite VC dimension is necessary and sufficient for learnability. But for robust learning, so far our work shows that finite VC dimension is sufficient for robust learnability, but we also actually show that it's not necessary. So an open question here is, what are necessary and sufficient conditions for robust pack learning? In terms of sample complexity, we know that in standard pack learning, the VC dimension exactly characterizes the sample complexity. In terms of robust learning, in this work, we show that the sample complexity is upper bounded by the VC dimension times the dual VC dimension, which is at most exponential in the VC dimension. So an open question here is whether the dependence on the dual VC dimension can be removed, and whether we can establish optimal sample complexity. Okay, we got stuck. Oh, sorry, yeah. Okay, cool. So in summary, we show that there are VC classes that can't be robustly pack-learned if you just use proper learning algorithms. But we also show that for any VC class, we can robustly pack-learn it if we use an improper learning rule. And the takeaway message is that we should start considering improper learning in adversarial robust learning, so in neural nets, deep learning. And yeah, please attend our poster 161. Thank you. Yes.
Sorry, so then what is robust harder for it than regular learning? Why is this finite distribution not necessary for the other?
Sorry, can you repeat it?
Yeah, isn't robust learning a harder for it than standard learning? So that's why isn't finite distribution necessary just because it's the regular learning?
So the case is okay. So yeah. The question is, why is intuitively it might seem that robust learning is harder than standard learning, and so how is it the case that finite VC dimension sometimes is not necessary? So there are situations where basically, because we are comparing with the best in the class, we're talking about agnostic robust pack learnability. So the best in the class might actually have really bad robust risk. Yeah.
My question is about the definition of robust.
Yes.
You said that there are those sets in which different sets of perturbations. I mean, what is the general form of those sets? Can I define those sets in terms of the underlying probability distribution and not in terms of geometry?
Okay, so yeah, we defined the adversary or the perturbation model before we even start learning. And it's basically a map from X to a subset in the space X. And the only requirement we have is that it's non-empty. So yeah, but once we fix the adversary, then we can talk about robust learnability with respect to this adversarial model.
It's not robust, and a natural notion would be that the probability under the underlying data
Mm-hmm.
that you will misclassify is small. That's not what you're...
It's actually more, it's stronger, because so we require that we answer correctly on points in the support of the distribution, but also on things that might lie outside the support of the distribution. But they have to be constrained in some way based on the adversary U. Yeah. Yes.
Let's take the rest of the question to the poster session and thank the speaker again.
Thank you.
Our next speaker is Yu Cheng.
All right, so I'm going to talk about